In today's lesson, we are going to start looking at statistics again instead of the probability that we've been focusing on for the past little while. Now, if we remember from early on, we talked about statistics as being able to take a look at data and infer information about our population from those data. When we were dealing with probability, we were making assumptions about the population and then using that to compute what we might observe in a sample, calculate different probabilities of different outcomes. But with statistics, we have the outcomes and we want to back solve for what's happening in the population. Now, we spend a lot of time during the probability units talking about different distributions. And the reason that that's going to be useful for us is that these distributions are going to come up as good models for what might be happening with our data. But in order to use a specific distribution for a real world data set, we need to know, does it look like our data are coming from a particular distribution? And so with today's lesson, we're going to be focusing on how we answer that question. In particular, we're going to be talking about what are known as probability plots. And the goals for the lesson today are to understand the construction and the use of a probability plot. So both how do we draw these plots and also how do we read these plots. And then we want to be able to actually read and draw the conclusions from them. So not only do we want to know how is it going to happen and how would you go about using it in practice or in theory, we also want to be able to do this in practice, right? And so what is really the purpose of the lesson? Well, if I were to hand you a data file that just has raw numbers in it, and I asked, are these data normally distributed? How would you go about answering that question? Right? Obviously, it's not useful just to look at the numbers by themselves, right? That's not going to give you too much of an assessment of that. And so we need different ways of summarizing the information. And we saw earlier in the semester that summarizing the information graphically becomes an effective way of taking a data set and making useful information out of it. And so today's lesson demonstrates a graphic that is particularly useful for assessing whether a distribution seems to correspond to given data. If we wanted to know, does a particular data set follow a particular distribution, one thing we could try to do is plot the histogram, right? So we had talked about using histograms early on to assess the distribution of a data set. And so if the distribution of the data set seems to look like the theoretical distribution that we care about, maybe that's a good way. And this works a little bit. There are some drawbacks to doing it. And in particular, it's likely going to be a biased representation, right? Small deviations on our histogram are going to make things look very different, even if sort of under the surface, they're not that different. And there's a lot of choices that we have to make during plotting, right? We have to decide on our bin size. We have to decide how discretized is it going to be. We have to decide, do we want equal or non-equal bin widths and so on. And making different choices there is going to lead us to very different looking histograms. And so because of that, these aren't going to be the best tool for assessing does a distribution fit. It's going to lead to erroneous conclusions somewhat often. Instead, we're going to turn to what are known as probability plots. Now, you'll actually probably see these called QQ plots more often than probability plots, but your textbook calls them probability plots. So we'll use that language here, but just know if you're ever out in the wild and you see a QQ plot, it's the exact same thing. Now, with a probability plot, our idea is basically that if our data are actually drawn from a particular distribution, then the sample percentiles and the theoretical percentiles should line up approximately. Right? So if you're actually selecting data from a normal distribution, then if you were to compute what are the theoretical percentiles for this normal distribution, those should be observed inside of your data as well. So the basic process that we're going through here is that if we compare the sample percentiles to the theoretical ones, we can assess, does it look like this theoretical distribution fits the data well? So if we were to order our data set from the smallest to our largest, these are the values that are going to correspond to our observed percentiles. Right? Each of them is going to correspond to some sample percentile. And the question is, which percentiles do our data correspond to? And this is one place where different sources are going to give different answers. I'll go with what's in your textbook, but just know that some people are going to say that your lowest data point is going to be a different percentile than this, and that's okay. At the end of the day, all of these methods are going to look approximately the same, and as our sample size continues to grow, they'll all correspond to one another eventually. In this course, what we are going to do is say that the ith smallest value is the I minus 0.5 over nth percentile. Right? So let's take an example. So if we have 10 observations, then the corresponding smallest value is going to be the 5th percentile, right? And how do we get that? Well, just to write this all out. So we have n equals 10, I equals 1, right? So if we take I minus 0.5 divided by, in this case, 10, right? Well, this is going to be 0.5 divided by 10, which is 0.05, or the 5th percent. Right? That's 5%. Now, if you have the 10th in this case, you'll have 10 minus 0.5 divided by 10, and so that's going to be 9.5 or 95%. Right? And you can work out all of the values between as well. Of course, if you change n, or you change which of your data points you're looking at, you'll get different values here. So what we're saying is that when you observe your sample, your 10 individuals, we're going to say that the lowest value in your sample of size 10 is going to correspond to the 5th percentile. The next one is going to be the 15th, and so on. And from there, we can take a look at the theoretical percentiles, right? So if you're comparing against a normal, you can say, what's the 5th percentile of a normal distribution? And then, if those correspond to one another, it seems like the distribution fits well. Now, instead of just comparing the differences, what we do instead is we plot them. We say the lowest value has a certain value, and the 5th percentile from the theoretical distribution has some value. And because we expect that they'll be equal to one another, or at least some constant linear relationship away from one another, if they're falling on a straight line, then we say that the distribution fits well. So we can take a look at an example here, right? Along the y-axis, we have the values in our sample, right? And these are ordered from smallest to largest. And along the x-axis, what we've done is we've computed the corresponding percentile from, in this case, a normal distribution, right? And so at our very smallest point, we computed however many n is, and I think n in this case is probably either 100 or 1,000, but it's not the most relevant in the world. And so we compute what percentile does that correspond to. And then we calculate the normal value that equals the same thing. And we plot that point there. And then we do that for the rest of them, right? So we have the observed values along our y-axis, the theoretical values along our x-axis. And you can see in this case, it almost perfectly lines up along that straight line, right? And so in this case, we'd say there's a really strong fit between the theoretical distribution and the sample that we've observed. All right. Now, if we reduce the sample size a lot, right, we're going to see here that we still sort of see a fairly good fit, right? We're a little bit further away from the line here, and so maybe that's going to lead us to question a little bit. But on this plot, we still are roughly near the line, okay? And so here, you might want to think about, are we using exactly the correct distribution? Should we maybe be considering a t-distribution instead? And we'll talk about t-distributions later on in the course. But here, it's not so bad. You see some issues in the tails. The line looks okay. If we take a look at this instead, now we're totally off, right? So here what we can see is that if you're too high or you're too low, it's not even close, right? We're way away from the line. We have this S-shaped pattern instead. That's not going to be the correct fit. And so if you were to plot and you see something that looks like this, you know immediately there's no way that this is the correct distribution for these data. We need to figure something else out. All right. Take a look at this plot as well, and you can see that we have this U-shaped curve coming up, right? And it's the same issue. In the middle, it might look okay, but as soon as you zoom out and you look at what's happening with the tails, this is clearly not the right distribution. Again, we're nowhere near that straight line. Now, this one's a little bit more interesting, right? Because here we see sort of a better alignment through the middle. We don't see nearly as dramatic of an S pattern or a U pattern. But if we're thinking about it, the tails of this distribution, so say below -2 and above 2, are quite far off, right? We see that there's this way in which the theoretical distribution is just not right for those values. We are getting smaller values than would be predicted on the negative end, and we're getting higher values than would be predicted on the upper end. And so what this is really telling us is that while this distribution looks like it's probably approximately the right shape, we need to have heavier tails. We need it to be there to be more probability of a more dramatic event. So a graph like this is also not going to be a great probability plot. And so the more of those plots that you take a look at, the better sense you'll start to get for reading them, right? We're looking for that straight line. It's not always going to be perfect, especially if we have a small sample size. But the question is there sort of discernible patterns of behavior that deviate from it? Do we see an S shape? Do we see a U shape? Are the tails too heavy, right? And using this is going to be our primary tool for assessing, does this seem like a reasonable assumption to be making about our data? And it's never going to be a specific science. It's always going to come down to a judgment decision. But this becomes an effective way to either bolster your argument that indeed the data that we have collected look like they're from this distribution, or no, they're not. We need to come up with alternative methods. And because so much of what we're about to do is going to rely on distributional assumptions, this is going to be a really powerful tool for ensuring that you're using the correct statistical tool whenever you're applying these methods. So to recap, probability plots plot the sample percentiles against the theoretical percentiles. They're useful to determine whether data approximately follow any given distribution. And when we're looking at them, we're looking to see, does the plotted points fall on that straight line or not? And if they do, probably is okay. If they don't, we should be looking for other distributions. So we're going to continue into looking at more statistics in the coming lessons, and I hope to see you all there.